Hello, everyone. It is my great pleasure to share our work, EasyView, enabling and scheduling tensor views in deep learning compilers. And I'm Lijuan Jiang. Firstly, I'll briefly introduce the background of the work. Then, the compiling pipeline of the work will be elaborated. Next, I'll expand on the compiler implementations and optimizations, following which some experimental results will be presented. Finally, I'll give some conclusion. In recent years, in deep learning applications, many novel neural networks have evolved model structures where layers comprised of memory-intensive operations might account to a considerable time proportion in both training and inference. Besides, as for memory-intensive operations, enormous device kernels could be called, each of which handles slight computations but brings in significant overhead, such as kernel launching and host device context switching. With layers characterized by memory-intensive operations becoming dominant in the efficiency of running neural networks, optimizing memory-intensive operations is getting meaningful and urgent. Automatically fusing memory-intensive operations based on just-in-time compiling techniques proves to be efficient, and enlarging the operation fusion scope of the compiler is quite appealing to optimizing current neural networks. In particular, memory-intensive operations on tensor views are ubiquitous in neural network implementations. However, mainstream solutions in state-of-the-art deep learning compilers exhibit imperfections either in syntax representations like XLA or operator fusion like TouchScript. The deep learning compiler TVM has gained prominent performance on operators in deep learning applications, and plays a critical role in multiple device deployment. However, views need to be loaded into different tensors in TVM, which constantly require new memory space and fridge expensive memory resources away. Besides, non-SSA view syntax cannot be intuitively expressed, especially for in-place update of indexing operations. Tensor views enable various data interpretations of memory space without data copy. As shown in the figure, views of the same tensor reference data of the same memory space differently by specifying the metadata of shape, stripe, and offset. Operations on views interact with the underlying data of the corresponding memory space. Modifications in values of views also modify the values in other views of the same tensor. There exist various view formats like reshape and transpose. Typically, basic indexing like slice also returns tensor views. Hence, we propose EasyView, which aims to enable and schedule tensor views in an end-to-end workflow from neural networks onto multiple devices. How we lower sophisticated view syntaxes to maximize memory utilization and schedule tensor views on devices is crucial for machine learning systems. Here, we highlight some compiling stages of EasyView. The tensor views are categorized into 7 types for error lowering considering various contexts. In order to optimize memory utilization, we keep the reference semantic in the lowered representations. Reference semantic allows modifications in a view without any modifications on other views. Hence, We need to track memory activities by analyzing data dependence of read and write operations so as to keep the consistent read and write order with the source code. Besides, we use TensorRef as the Lord IR of TensorViews. TensorRef consists of address, shape, stride, offset, and data type. Views of the same tensor are loaded into different TensorRefs, which share the same address, but differ from shape, stride, and offset. We also include a vector called DDE in TensorRef to keep the read and write operations on the tensor data for memory activity tracking. In this section, we will expand on compiler implementations and optimizations of EasyView. Firstly, about the tensor categorization. The categorization of tensors is primarily based on whether the tensor view varies the metadata such as shape, stride, and offset. Next, whether the view context modifies the underlying data is the other consideration, since read operations retrieve the correct values should be ensured. According to the analysis of data dependence of read and write operations, including read after read, read after write, and write after read, 7 tensor types are categorized, which are enough to keep the consistent read and write order with the source statements and keep the correct metadata in the meanwhile. More specifically, TWD represents the tensor situated at the definition operation. TRD and VRD represent tensors and views respectively, whose underlying data is read in the subsequent operations after the definition, and never been modified after the definition. TWS and VWS represent tensors and views respectively, whose underlying data is written in the subsequent operations after the definition. TRS and VRS represent tensors and views respectively, whose underlying data is read in the operations following the subsequent write operations after definition. Secondly, about the view lowering process. The lowering of the tensor views into TensorRefs consists of TensorRef generation, memory allocation, and the variation of shape, stride, and offset. The definition of a tensor corresponding to TWD generates a new TensorRef and allocates new memory space based on the given shape information. The lowering of views corresponding to VRD, VWS, and VRS generates new TensorRefs, which refer to the allocated memory space instead of new memory allocations. The generated TensorRefs keep the shape, stride, and offset of views. Last but not least, multiple writes to the tensor also cause several contexts to generate new TensorRefs for tracking memory activities, which correspond to all tensor types except TWD and TRD. As shown in the figure, the tensor Cs corresponding to the tensor type VRD, VWS, TRS, and VRS in stages 3, 4, 5, and 6 respectively all generate new TensorRefs. Besides, since stage 4 corresponds to an in-place update on tensor C, no memory space is allocated. Memory activities are tracked in the lowering process for successional code optimizations. Multiple writes to the shared memory space require that the traversed topological order of operations need to keep the consistent read and write order with the source code. The tracked memory activities correspond to data dependence of read and write, including read after write, and write after read. Read after read is not included since the order of read operations would not affect the correctness. If the current load stage includes a read operation to the memory space, DDE of the corresponding tensor ref tracks the last write operation to the memory space up to the current load stage, which ensures the correctness of read after write, like the tensor types of VRD, TRS, and VRS. If the current load stage includes a write operation to the memory space, DDE of the corresponding tensor ref tracks all the read operations from the last write operation to the current load stage, which ensures the correctness of write after read and write after write. When there do not exist read operations from the last write operation to the current load stage, DDE tracks the last write operation, which ensures the correctness of write after write, like the tensor type of TWS and VWS. As shown in the figure, TensorRef C1 tracks the definition operation corresponding to stage 1. TensorRef C2 tracks the read operation corresponding to stage 2 and 3, while TensorRef C3 and C4 track the write operation corresponding to stage 4. The directed acyclic operation graph is generally constructed, whose topological order is used for schedule primitives embedding on devices. The operation graph is constructed based on the data dependence due to the read and write of the memory space. The nodes of the operation graph are operations, while the edges are tensors. The source of the edge is the operation, which modifies the tensor data, while the end of the edge is the operation, which reads the tensor data. As shown in the figure, the topological order presents that stage 4 is traversed after stages 2 and 3, and before stages 5 and 6. After we lower the tensor views and construct the operation graph based on the tracked data dependence, we could get the topological order by traversing the operation graph and embed schedule primitives on operations. The majority of memory-intensive operations in modern neural networks are element-wise and reduced operations. The fusion types in this work mainly include injective-to-injective fusion for element-wise operations, which is profitable for memory-intensive subgraphs, and schedule primitives of loop fusion and operation inline are mainly applied. As shown in the figure, operations are traversed from the bottom up. Operations in terms of views are inlined due to the complicated index computations. Besides, operations characterized by views related to the same tensor are traversed and inlined based on the data dependence kept by the tensor refs. Otherwise, loop fusion is applied, which holds intermediate data in registers and benefits on-chip data reuse. Operation inline is refined for tensor views in basic indexing since item assignment modifies a portion of underlying data. The tensor data might be composed of several modifications due to multiple writes. In the refined operation inline, a nested conditional expression will be generated by recursively backtracking write operations based on the tracked data dependence. Besides, the conditional expression is based on checking whether the indexed dimension satisfied the indexing formats. On the other hand, as for memory optimization, several TensorRefs might share the same memory, and an index flattening path is applied to TensorRefs based on the metadata of shape, stride, and offset. In this section, we'll present some experimental results. Firstly, we present how the fusion of operations in terms of tensor views influences the performance by analyzing hotspot functions from popular neural networks. The average speedup of the performance of hotspot functions with just-in-time operator fusion and with scheduling views over that without just-in-time operator fusion reaches 9.28, and a speedup of 5.14 is achieved by scheduling views. Besides, the average reduced memory allocation reaches 35% with respect to views. The experimental results show that the more operations with views contained in the hotspot functions, the higher performance improvement could be achieved. Here, we give an example. The function offset to big box achieves speedup 12.61 with 18 operations in terms of views. Besides, the function offset to big box is divided into eight device kernels due to operations with views, and the number of generated kernels could be reduced to 1 due to the support of views. The reduced memory allocation of the function reaches 29% concerning views. Besides, the experimental results also show our proposal could get an average speedup of 5.63, 2.44, and 4.67, comparing the performance of EasyView with that of XLA, TouchScript, and JX, respectively. As listed above, the lacking of operator fusion in terms of views in basic indexing of TouchScript reduces opportunity for performance improvement. Hotspot functions with more basic indexing operations could achieve larger speedup with EasyView. Besides, since XLA lacks the support of item assignment, functions with item assignment, like valid flags, cannot be automatically optimized by the compilers of XLA and JX. We also tested the performance of end-to-end neural networks. The figure illustrates the performance of three typical object detection neural networks, i.e. mask-CNN, SSD, and DETR. And the experimental results show that 8.002, 8.02%, 6.5%, and 4.51% performance improvement due to scheduling tensor views for mask-CNN, SSD, and DETR, respectively. Finally, we'll give some conclusion. Deep learning compilers have been a significant force to drive the development of AI systems. Automatic fusion for memory-intensive operations based on just-in-time compiling techniques could greatly benefit the deployment of neural networks. In this article, We focus on the operation fusion in terms of tensor views. We keep the referring semantic of views in the Lord IR to optimize memory utilization. We also design a logging algorithm to check the read and write data dependence for code optimizations, considering in-place updates. Besides, scheduling strategies are also designed and implemented to fuse view operations in deep learning compilers. Experimental results show prominent performance improvement and achieve competitive results compared with the other popular deep learning compilers. Thank you for listening.